Assalamu alaikum. So this video is about binary numbers and using bitwise operations in C, C++. And I'm going to follow this appendix from the book Tony Geddes. And this is actually Appendix I, which you can see or download from the internet. So this explains very well how binary numbers are represented in the memory and how we can do bitwise operations. So let me go through this. So we have these basic integer data types like character, integer, short, long. Where on these data types we can apply bitwise operations. First of all, let me explain how they are represented in the binary form. You need to understand that we have bits starting from the right hand side, and that is called the low order bit, and as we move towards the left, they are high order bits. That's obviously they are named like so because this bit has the least weight or value, and the bits on the left sides have more weight or more value. The also to remember is that when we say bit 0, it is the actually the first bit, and bit 7 would therefore will be the eighth bit of the binary representation of that number. So if you look at that, if you look at different weights at each bit of that number, so bit 0 has got weight 1, bit 1 got weight 2, and so on. So it's basically 2 raised to power the bit position. So if you say 2 raised to power 0 is 1, 2 raised to power 1 is 2, 2 raised to power 2 is 4, 2 raised to power 3 is 8. So actually it's the bit position, which is raised to power 2, that gives the value at that place. So that means that if we have a number, for example, 0, 1, 1, 0, 0, 1, 1, 0, that means that at bit level, bit position 0, the value is 0. That means it doesn't contain any weight. But where if you look at bit position 1, the value is 1, which means that bit position 1 has to be counted. So it means that its weight is 2. Similarly, at bit position 2, if value is 1, then that would also be counted. And its weight is 4. So it's really 1, 2, 4, 8, 16. So doubling the number, the next number. So if you look at this number, so we will only add the values or the weights where the bit was 1. For example, if this is bit 1 is 1, so we will add 2. Here is 1, we will add 4, and we will not add these values because they would be multiplied by 0, and we will not have any weight for this. So bit number 5 is 1, so we will add 32, and then the last one is bit 6, which is 1, and that weight is 64. So if we add up this number, we get 102, and 102 is basically the decimal representation of this binary pattern. So it's like this one. So this is brief introduction about how binary numbers are stored or represented and how they are related with decimal system. In C, we have different operators where we can apply operations at the bit level. So first of all, let me create a small program where I will assign value 102, an integer where I will get well, I will assign value 102 to that variable, and then I'll see how this could be shown. So so if I declare a variable int n, um, and its value is 102, if I say cout, and so it would definitely show 102. But what I'm interested in is to display it in this binary form. So we don't have um, any direct conversion, like we can convert it into hexadecimal or octal values, and then display that using C manipulators. But for binary numbers, we don't have any manipulation kind of thing, so we don't have any manipulators to display the binary pattern. One we can use a library which is called bitset. So if I include a bitset library, um, here we can do like create a type which would be represented in binary format. So basically, it would not be basic conversion, but now we are creating a type of kind bitset, and then we tell here that how many bits we want to use. For example, represent this number. So usually it would be like 8 bits would be a good start. We can say 10 bits, 16 bits, 32 bits. So it's our choice. But then I say bit set, and then I will create a new data type. We can call it a new data type. For example, uh, new representation of the same type of data. So let me say in bits. So this would always display values in bits. Okay. So if use this variable, if I say in bits is equal to n or 102, whatever I write, I can also write 102. So that means this value would be assigned to this type that we have just created, and that means that now this in bits would be treated by cout in a different way, and that would not display it as an integer value, but rather it would display it in binary pattern. So if I display it in bits, now in bits has 102 here, so that will display me the binary pattern for in bits like this one. And if I see from the guide here, so you can see it says 011, 011, 00110, 00110. So it's the same value that we have seen. So it would be a good start to know that okay, bit set we can create a type bit set like for 8 bits. So for example, if I do it 16 bits, so it would still be the same number, but represented in 16 bits. So I have like up till here, they were 8 bits and then all zeros after that because they will not have any value. We can change it as well to 32 bits or 64 bits. And size of this variable would change accordingly. So if it is like this one, it will only take 4 bytes, and then if I move it to like 64 bits, it will take 8 bytes. But that's another story. But this will help us to see how different values are working. So this was just the introduction of how we can use this for representing binary values. So next, let's see. Okay, let me continue with this, and then we will um, discuss different binary operations operators that we have in C++. The first operator is the ones complement operator, which inverts all, like it changes all bits. If it is zero, it will be changed to one, and wherever it is one, it would be changed to zero. So the operator for that is this tile symbol. So if I say, so we have already shown it here in bits like this one. And if I say now n is equal to uh, the inverse of this number, so of course what this operator would do, it would convert or change, toggle all bits, and then that value would be stored in n. And then we again say that in bits equals to n and display it again. So after changing this, just to see that how it works. So if you see the output here is like all the bits are toggled, right? So the ones which were zero, they are now changed to one, and the ones which were one, they are changed to zero. So and of course, I can always write its decimal form. So for example, I could write n and then separated by this so that I know this is the decimal form of the value n. So same could be done for this. So we can see it's 102, and then this was the value, and then this is minus 103. So this is interesting to note that now this we know that all the negative values are represented where the first not the the highest order bit is 1. So that's how we represent negative values. And how this is done, this can be understood by reading this thing where we they explain that how negative integers are displayed or stored in the memory. So we have a concept of taking one's complement. So the thing that we have done here is it gives us one's complement, and that means that toggling every bit. But then we have another concept of taking two's complement, and two's complement is basically nothing except that we take the ones complement. So if you look at this value 2, if we take ones complement, all the bits would be converted or toggled, and then we get this. So this is a negative number, but then it is not representing minus 2. So this is representing plus 2, and one's complement is not representing minus 2. Rather, we will have to add 1 to it. So if we add 1 bit to this, we will get this number, and this is the correct representation of minus 2. So if ever you have to convert a number, for example 35, to minus 35, how you can get that, how that would be represented in the memory. We first take one's complement of 35, and then we add 1 to that number. The bit 1 would be added, not the decimal 1, the bit 1 would be added, and then that would give us minus 35. So this was taking one's complement, and the other operators are, for example, we have done this, I guess, bitwise AND operator. So what is an AND operator? We know about AND operator that it takes and it performs AND operation on two numbers, and then it gives us true or false. For example, if I say C out, and then I just for example I say 23 um, and any other non-zero number. So the outcome would be 1, because AND operator always give us a true or false, right? So if I just run this program, so you see it says 1. Okay, good enough. But if I say 23 and 1, like with single this and sign, and if I run this program, sorry, I have I have not added new line. So if I do this AND operation, oh, okay. Interestingly, it is also giving me 1, but if I say not 1, like 12, 12. So this is by chance, but otherwise this would always give 1 or 0, so true or false. But here you see it gives me 4. So what is this 4 value? It is how that value is calculated. It is basically by taking by doing AND operation on every bit of these on corresponding bits of these two numbers. Here it was like a non-negative value, non-negative value, and the result would be true. If any one of those values is 0, then the result obviously would be 0. But here, with bitwise AND operation, that means that we take we perform AND operation on every bit of each of those numbers, so both operands. So what does that mean? So let me explain it by again doing it. Okay, if I say um, in bits, if I assign this 23 and then C out in bits, and next I say just to see how these bitwise operations are working. 23, and then next one is 12, and show this, so that it will help me understand how this evaluated to value 4. Um, if I run this program now, so you see here, so these are the numbers that I am performing AND operation. And here, if you look at this 1 0, so uh, uh, the low order bit would result this the, the resultant bit would be 0, then 0 here, and then 1 here, and then 0 here, 0 0 0 0. So what we get is 0 0 1. So actually 1 0 0 is 4. So that's why it displayed 4, and that 4 was displayed in decimal form. That's why it showed me 4. But I could, for example, write instead of this, I could have written um, int result, and result is equals to result here. So this would perform AND operation, and that will be stored in the result. And this shows me 4 again, right? But I can also say um, if I want to see that in bits, so I just assign this to in bits to result, and then show it, and we know that it is showing me 4. So you can see it here. So now it is shown in bits. So 1, 2, 4. So 4 is 1. So all others are 0. So it would be 4. So this is bitwise AND operation. And exactly same is the case with the OR operator and XOR operator. So just to remember, like if I can just change this to um, I can just take the same things for the OR operator, just to explain that, okay, this is the result of OR operator. So, so in bits, the same kind of logic, everything same, except that I just change it to OR operator, right? And here would be OR operator. But of course, I will get an error because this is a redeclaration. So I just make another block to make it a local scope for this, so that it doesn't report me any error. Um, so with the same values, if we from here onwards, like this is the first number, which was 23, I guess, and this is the second number. And with OR operator, what we are getting is 1 or 0 is 1, 1 or 0 is 1, 1 or 1 is 1, 0 or 1 is 1, and 1 or 0 is 1, and all others are 0. So that makes my number equals to, So if I have like shown displayed it in bits, but I could have written, for example, result. So basically, this is the value 31. But if we would have applied, like before, if we would have applied um, this operation straight away, just like before, I missed this statement. If we would have applied 23 or 12, this means that these both are non-zero values, and this would definitely give me a true answer. So it would give me true answer. But when we apply bitwise operation, then it is totally a different value. So this is true, but here, so if we apply non-bitwise version of OR, then these two numbers would give me one, which is like true and true is true. But if I apply bitwise operation, then every bit would be a bitwise operation would perform OR operation on every bit, or every corresponding bit of these numbers, and then we get this value. And this, when it is converted into decimal, it gives me 31. So at the end of the day, it's how I display it. If I display it like if I display result, which is an integer variable, it would display 31. But if I display in bits, actually the value in the memory is same, but it would just display it in a different way. So it's not converting anything, but it is just displaying it in a different way. So this is about the OR operation. And similarly, I can just copy this code and run the same for XOR operation. It's just the thing that you need to know is how XOR operation is uh, performed in C++. So I use XOR. So here we don't have XOR here. So for example, I just say um, let me remove this first. Then I say 23, or instead of OR, we use XOR. So for XOR, we use caret symbol, and I have to find where it is in my keyboard because we don't use it too often. But this is the caret symbol, and this will again show me how this is performed. So XOR actually is that the similar bits would get zero. So that is the logic. So for example, here in this code, you see these two. Um, this let me fix the alignment. So hopefully this will fix the alignment somehow. Okay, so these are the numbers where I am doing XOR. So if you and if I this value is basically 27. So how we are getting this value is one XOR 0, and that truth table you can look for XOR truth table, and if the values are different, then it would produce 1. So 1 and 0 are different, so we get 1. But here 1 and 1 are similar, so we get 0. And then 0 1 would produce 1, 1 1 this 1. But if they are similar, whether it is 1 1, it will give 0, and if it is 0 0, it will give 0. So similar values would produce 0. So this is the XOR operation. So these are three main, or rather four main bitwise operations like XOR and OR and NOT, which was one's complement. So next interesting thing is how we can do different, how we can do different operations on different bits of this number. So for example, if we have um, Okay, so this was the problem that you had in your assignment, where you could you were asked that, okay, we have a a number, a big number, an integer of 32-bit value. So this would be an integer with these 32 bits, and we know that this is bit number 0 and this is bit number 31, and it tells that the first 7 bits, like from bit number 0 to bit number 6, they are the belt number of this army person, and then the next 10 bits would be the batch number, next 5 bits would be the log number, and last 10 bits would be the unit number. So if we could figure out, okay, this was the required program, so where you had to say ID of the army man, and this is an integer number. So what you had to do is, so this, you take this number and see what how that is represented in the binary form. So it, like, if I put 8 5, so let me do it quickly. So Control C, and if I say um, um, just a minute, so I just copy this. Okay, personal data. Okay, so if I say the number was this one, and we want to see this number in bits, I just delete this all. So that would be like, it's not in it's 16 bits. So if I just change this to 32, for example, then of course whole program would change. But here you see this is the number in binary format, right? And what you had to do is, if you look at the problem statement, it says that first 7 bits are the belt number. So for this number, the first 7 bits, what are the first 7 bits? You can see like 0, 1, so first 7 bits, right? 1, 2, 3, 4, 5, 6, 7. So up till here. So this is the belt number. So that should evaluate to 51. So belt number should be like, if you convert this number 0, if you convert this number to decimal, sorry, 2, 3, 4, 5, 6, 7. Control C. So I put binary here. And say, okay, this is the number. So you see its corresponding decimal value is 51, right? And that's what you have to find. So this is 51. So this is something you needed to find. How you could do that? You had to, for example, there are multiple ways, but one way would be to check this bit, of course, you will have to do it 32 times if you are not using loops. And at that time, you were not allowed to use loops. But you check this bit, and then you get a number. And then you get check this bit, and then you make a number. Then this bit, and this bit, and this bit. So, for example, if I want to do it, I would do something like this. So how we will do that? So the thing is that if I run this program, let us make some logic here. So if I run this program, so this is the personal data, right? So what I have to do is I have to check whether this bit is on or off. Whatever the answer is, if it is on, like if I do AND operation at this place, if I create a mask, one for this place, and then all others would be zero, of course. And then I perform AND operation, and I will get the this bit on for this place, and then that would show me that this bit is on. So let me do that. So first I say int mask, and um, I start with mask equals to 1. So that is the first bit, right? And then I need to have a result variable, int result, and I say that my result of this masking is a, and if I do a and mask, that means that I will get the result, and that would be that would have 1 at this place, if in case this bit is 1, or 0 at this place in case this bit is off. So all others bit would be off, of course. So that is my result. But then I have to check, I have to create my belt number as well, right? So belt number is, we start this with 0. That is important to start it with 0. So I say belt is equal to belt or result. So whatever result we get at that particular place, so this is like bit number 0 we are talking about right now. So that would give me the belt number. So let's see. So if I do this and then I display cout belt. So if I run this program now, so it would check. See, so it checked this one, and this was 1, so belt got 1, right? So next time, if I do this for the second place as well, and so what it will do. So if I run this same code second time, of course, I will not use loop here because that was not allowed in the assignment. But if I say second bit is mask 2, so that means that it would either give me this result would either give me 0 0 0 0, and the last two bits would be like 1 and 0, 1 and 0, or like we are creating this mask 2. That means the bit number 1 is 1, and all other bits are 0, and that means that result would be 1 same mask in if that bit was on, or all zeros if that bit was off. And if we do the OR operation with the previous result, which was the belt result, if we OR that with this result, then that would be the updated belt. So now this bit would be set accordingly, like 0 or 1. That would be set. So if I run this program for the second time, you see, so this bit was also on, so that means this number is like now belt has 1 1. So I have dealt with two bits right now, right? So I can repeat this code more times to get the required, because I know what the belt number is. How many bits this belt number will take. So next mask would be position 4, next would be 8, next would be 16, next would be 32, and last would be 64. That makes it 7 bits. So the last one is 64. So now if I run this program, it will give me the correct belt numbers. You see, so it has done it step by step result. I could have printed it, or you can see by debugging that how it looks like, but you see I have got 51 in the belt number. And this is exactly what we wanted for this 7-bit belt number was 51. And if we do the same logic for next 10 bits and then 5 bits and 10 bits, so we can figure out all those values. And that was all about the assignment question that we gave, and I hope it would be interesting now. With this, thank you very much. Take care. Allah Hafiz.